Okay, we are recording. We are live. Welcome to Steel Design. We only have, like 3 or 4 lectures left, and then that's it. Because next Friday is our final exam review, and then we are done. Let me turn off my email client so that doesn't disturb us. A couple of updates. First off, let me copy a couple things in the chat. So if you go to the chat, I have the links for the 2 surveys, the course learning outcome survey where we assess the outcomes for the class, and then the university administered survey where you evaluate the class and me. I put those links in the chat. I'll also put where we're at right now in terms of response rate. Again, if you upload proof, you'll get a little bit of bonus points on that that you did it. Again, you can say I'm the worst professor ever. I just want to see that you've done it, and you'll get a little bit of a bonus on that. In terms of where we're at on grading, all the attendance grades up to date. I've been trying to do that, before every lecture, so everything's current now. 6.4 is still being graded. That was the assignment on CB, but I posted the solution to that as well. 6.5 though is assigned today. That's going to be your first assignment on discretely braced beams. Today, what we're going to do, I have, I guess, maybe a slight typo in my slide because this says examples 1 of 2, but really what it should just say is both of them. Or maybe I'll just delete that because if you recall last time, we started an example, but we didn't finish it. Well, today we're going to finish it. We're also going to do a second example on LTB, and then we're going to introduce design. When I say introduce design, I want to show you the design aid and kind of how it works. I will forewarn you that the design aid that we use, table 310, looks like a nightmare. It does. It's not. It's actually pretty easy to use. If you open up the FE reference manual for the exam and you go into the civil engineering section, you will actually find a snippet of this table in the manual. So it's a pretty standard aid. It looks scary. It's really not. And so I'll help you navigate that a little bit today. But let's go ahead and just advance a little bit. I'm not going to spend too much time in the PowerPoint because we're going to go back to the example that we did. I just want to make sure that everybody recalls our process for determining Ltb capacity. Remember, what we do is we first have to identify whether or not we're in zone 1, zone 2, or zone 3. And so that's a function of our unbraced length, the distance between the braces, and then whether or not that's either less than or bigger than LP or less than or bigger than LR. The LP and the LR are the 2 anchor points. And so if you're less than LP, you're in zone 1. If you're between LP and LR, you're in zone 2. And if you're bigger than LR, you're in zone 3. And based on each of those zones, there's a pretty plug and chug process to compute the capacity. The big thing, the big sort of variable, if you will, is the effective CB. CB has the potential to augment the capacity that the equations give you beyond MP. And what the code says is I don't care what CB does, the capacity is always limited to MP. So whenever you look at the zone 2 and the zone 3 calculations, the FEMN, the moment capacity, is always the minimum of whatever the expression gives you and MP. And the other thing to keep in mind, and we're going to talk about this a little later, is that everything that we're looking at here in this flow chart is just this. It's just the Ltb curve written in equation form. So all you're doing basically when you use these expressions is you're trying to figure out what the capacity is on this curve. That's really all you're doing. Here's our sort of flow chart, if you will. Everybody good on this so we can get back into the example? Any questions? All right, I'm going to take that as everybody's good. So let's get into our example. So this is the example that we were working on last time. We were trying to determine, this is an analysis example, so we're trying to determine whether or not the beam has adequate flexural capacity, shear capacity, and a deflection limit. And what we focused on last time was computing the moment capacity, but we didn't finish the example. I'm going to try and knock that out pretty quickly today just to make sure that we tie it into what we had done before. And a lot of what we did before with continuously braced beams is still going to be the same, right? It's still going to be the same shear capacity. It's still going to be the same deflection check. It's still going to be the same structural analysis. The only thing that's different is that FEMN computation. So that's what I really wanted to hammer home. And then after this, we're going to do another example that, spoiler alert, is going to be in Zone 3. So with Zone 3, there's really no nifty aid. You just have to sort of chug your way through it. I mean, say what you will about the equations in Zone 2, but we're actually using a lot of shortcuts, like that BF term, that beam factor. There's a lot into that. It's the difference between your MP and your MR and the difference between your LR and your FP. There's a big computation that goes inside there, and it just does it for you. So it makes your life a little easier as an analyst. But for Zone 3, there's no real shortcut. You just kind of have to chug your way through it. Because you look at the equation, it's not hard, but there's just a lot of variables that go into that. Okay, so with that, I'm going to go ahead and chug our way through this example. Let me stop the share and pull up the notebook. Give me 1 second. So I'm gonna first off scroll up and just sort of walk through the capacity check that we did so far. Now, one of the things that we really didn't hammer home super well last time, but we're going to talk about a little bit today, is the fact that we're really only evaluating one segment, okay? Remember, this beam has two segments. There's a segment from, if I use my highlighter, there's a segment from here to here, and there's a segment from here to here. So there's two different segments. Now, we're only evaluating one of them because from an analysis perspective, they're both the same. They both have the same CB value. They both have the same LB value. They both have the same maximum moment. So really, if one segment is fine, both segments are going to be fine. There's no reason to do both. If we had a beam with all sorts of different bracing, we'd have to do this calculation that we did yesterday for all of the segments. So because they're all going to have different parameters. That's just a minor point I wanted to bring up. Now, we looked up our CB value from table 3.1 because this was a simply supported beam with a uniformly distributed load. If you have a simple case, just look it up. If you have a little bit more of an intricate case, you have to go through and chug out CB, and I think by now we know how to do that. You just need to go through the motions. It's a 24 by 76, and the beam, the dead load shown includes the beam self-weight, so we don't have to worry about that. So what we focused on last time was computing the capacity. So we looked up the LP and the LR. The LP was around 6.8 feet, and the LR was 19.5 feet. When you compare that to an LB of 15 feet, remember that this is a key. There's a difference between the length of the beam and the unbraced length of the beam. The unbraced length of the beam is the distance between braces, and that's 15 feet. So it's clear that we're in Zone 2, so we use our Zone 2 expressions to compute the capacity. Here's our flow chart again, right? So I just copy and pasted it in there, and that was our Zone 2 expression. So all we needed to do was look up everything we needed. We had CB, we have our LB, we have LP, we have FEMP, and FEBF. We got those from the from table 3.2 from the ZX charts. It's already computed for us. And then you just check it out. So we did the upper expression, that big long equation, CB times that quantity there, and we got 733.5 foot kips. And so the capacity is the minimum of whatever you get from your expression and your plastic moment. And so the plastic moment for this beam was 750, so our flexural capacity is 733.5. So where we left off from the previous lecture is, we're looking at a 24 by 76. We know that Fy is 50 KSI, so that means we could use table 3.2. The loads shown include the self-weight, and we know our FEMN. Now, what I did right before class is I just went ahead and looked up the FEVN and the IX for a W24 by 76. I hope by now that we know how to do that. If you need to know where I got that, I got it on page 3-24. So this is in table 3.2 on page 3-24. So that's pretty straightforward. The only thing left to do is to perform the structural analysis to make sure that this beam is adequate and check its deflection limits. So what we're going to do, we're going to knock through that pretty quickly. So on the structural analysis side, we need the dead load moment, which is going to be WL squared over 8. And again, it's, what was that? Did somebody say something? Oh. Sometimes I can get echo from my microphone, so apologies for that. So we're going to do WL squared over 8, and the reason for that is it's a simply supported beam with a uniformly distributed load. Now, the one thing to keep in mind is that what is my L in this formula? I'll write this one out. So it's 1.25 kips per foot. What's L? I want to make sure everybody's paying attention. It's 30 feet. Yeah, we're using the actual length of the beam. This is structural analysis, so I care about, this dimension for the structural analysis. This dimension is LB. Okay, so 1.25 times 30 squared divided by 8, that ends up being something like 140, or sorry, hold on, didn't put my equal sign there, equals 140.6 foot kips, and then ML is WL L squared over 8, and I'll just do that one right here. That one's 3, so that ends up being like 337.5 foot kips. And then if I compare that to MU, which is 1.2, or not compare, I need to use those, 1.6 ml. I'm getting 708.75. Can anybody check me on that? Okay, so therefore, if I'm doing a check, I can say that MU is 708.8 foot kips, just to round. And then PMN was 733.5. So what does that mean? Help me out. What does that mean? Are we good? Are we bad? What does that mean? We're good. There we go. Now for the shear, we do the same thing. Now what I'm gonna do is this. I'm gonna say for the shear 1.2 times that plus 1.6 that. I'm just sort of compressing everything together. So, phi mn greater than or equal to mu. Exactly right. So, if somebody can do that faster than me. Oh, I have a typo there. I'm getting 94.5 kips. Can somebody check me on that? There we go. So, now we have VU is 94.5 kips. And then our PVN is 315 kips. And we got that, from right there, from table 3.2. So, again, we haven't discussed exactly how to compute PVN, but I will talk about that near the very end. It hasn't really been a big issue. I don't think I should just say, don't worry, it's fine. Like, I think you should understand the math behind it. But I think by now, hopefully, you're starting to see that, shear really isn't a problem. in building design. In bridge design it can be, but in buildings it just doesn't matter in most instances. What was WL? WL was 3 kips per foot. Right there. Speaking of live load, let's do a deflection check real quick just to make sure that we're all comfortable with it. So I'll just do that down here. So first off, we have a WL of 3 kips per foot. We have a length of 30 feet. We have an E value of what? Somebody's going to tell me what that is. And this is 2,100 inches to the 4th. There we go. 29,000 KSI. And so with all of this, I can determine the maximum live load deflection. And does anybody know that formula? Or where to find it? I'm going to give everybody a sec on this. I want everybody awake and table 3-23. And so exactly right. We're going to be in table 3-23. Now your formula, hold on, Mr. Romans. Your formula is a little off. Now you're correct on the 1728. That's correct. But you have basically WL over EI. And WL over EI isn't going to work for this beam. You might be looking at maybe the cantilevered beam or something like that. But we're going to be looking at case 1, which is the simply supported beam. And so for case 1, it's 5 WL to the 4th over 384. No, it's fine. It's fine. 384 EI. So that's, let's write out a big old fraction. So 3 kips per foot, 30 foot raised to the 4th, 384, 29,000 KSI, and then 2,100 inches to the 4th. And then don't forget we need a conversion factor in there. And so the live load deflection is, drum roll please. I say that, somebody's going to try and put it in the chat. I'm getting 0.898 inches. So is anybody else getting that? Okay. And so when you compare that against the deflection limit, and the deflection limit, I believe, was right here. A deflection limit of L over 360. So we're going to do L over 360, which is 30 feet over 360. But then we have to adjust that for units. And so it's 1 inch. And so the beam is actually deflecting 0.898 inches, and it cannot deflect more than 1 inch. So we're good here. So there you go. All right, are there any questions on this? I mean, hopefully this, like I know that the capacity stuff for FEMN, it might be a little new, but everything else isn't. It's all the same stuff. The shear calc's the same, the deflection calc's the same. It's just the moment calc. Everybody good? Now, one thing I do want to sort of point out, just sort of as a thought bubble, something to think about. So here's our beam, right? And what does the bending moment diagram of this beam look like? So here's the bending moment diagram. We'll call it the MU diagram in foot kips. It's going to go to 0, and it's going to go up like this, like that. And so that upper moment is 708.75 foot kips, right? That's what WL squared over 8 is telling us, is what that peak bending moment is at the top of the moment diagram at midspan. So if I look at this from a segment by segment perspective, here's segment 1, here's segment 2. Take a look at each of those two segments, right? So we'll call this segment 1, segment 2. So if I look at, let's say, here, let me give myself a little bit more room in my little thought bubble here. So if I look at each of these segments, so for example, what is the maximum MU for each segment? Well, it's 708.75, 708.75. That's the same, right? Do this, make it a little clearer. Okay, what about the LB? Put units on this. What about the LB? Well, this is 15 feet. This is 15 feet. What about the CB? Well, this was 1.3. This was 1.3. So analytically, both segments were the same. There weren't any difference between segment 1 and segment 2. So really what we did technically is we only analyzed half the problem. We looked at, say, segment 1. Segment 2's calculation would be exactly the same because none of the parameters are any different. But what would happen if they were? So this is just food for thought. So let me stop my share and go to the PowerPoint to sort of make this point. So, for example, I want to look at like the following beam, and this is a nasty beam. I'm just making a point about this. Now let's take a look at this, okay? This beam's a little nastier. So first off, it's not a simply supported beam. It's an overhanging beam, and we've got 4 braces, so there's 3 unbraced segments, and I purposefully drew this one out to be complicated, right? Each segment has different loads. It's got different lengths. It's got all sorts of different stuff going on. So in this problem, or in this situation, everything's different. Each segment has a unique MU, right? A maximum MU. So that would, when we compare phi mn to MU, for each segment, we would plot the moment diagram. We would take the maximum bending moment in each segment. That's how we would do our design check. But also, from a capacity perspective, each segment has a different LB value. And if you look at the moment diagram, it's going to be all sorts of all over the place. So each segment is going to have a unique CB. So what you would have to do is each segment would have a unique phi mn. And so what you would do is for like segment 1, you would take the phi mn, compare it to its maximum MU. For segment 2, take its phi mn, compare it to its maximum MU. For segment 3, take its phi mn, compare it to its maximum MU. And that's how you would do the moment check. For the shear check, you just take the maximum shear, and for the deflection, you just take the maximum deflection. But for moments, you'd have to do each one. As for which one governs, it'd be the one that has the largest performance ratio. So I'm just putting this out there for a thought experiment. Now, let me say this is a bit of an unrealistic scenario, but what is a realistic scenario is situations where you have, let's say, 3 unbraced segments and the ends are different than the middle, and so you might need to check both of them. So I'm just throwing that out there for a thought experiment. Again, I'm not making you do anything this complicated. I just want to make sure that you understand the science. Is there any questions on that before we get to our next example? All right, I'm going to take that as a no because I'm not hearing anything. If anybody has any questions, make sure and let me know. Okay, our next example is a lot shorter. No, good. This next example is a lot shorter. All we're doing is computing the phi-min for a W14 by 61. A couple of things about this example. So the unbraced length is 30 feet. I've given you the moment gradient modifier, the CB value, it's 1.5. The A992 steel, so FY is 50 KSI. One of the notes, I want to talk about this note here. A W14 by 61 is actually not one of the bold rows in Table 3.2. There is a reason for that, and that'll become clear here in a bit. So I'm purposefully not using a bold row, okay? Now I'm going to pull up my notebook here. I've done a little bit of the work for us in advance, and I'll show you what's up. Let me share my notebook again. So here's the problem. And like I said, I've done a little bit of the work for us in advance. First off, I want to focus on the unbraced length. So the unbraced length for this problem is 30 feet. Okay. So we're going to go to our ZX table. Now, if you want to follow along in the manual, you can follow along with me. I'm on page 3-25. And if you look down here, I highlighted the W14 by 61. And again, it's not a bold row. There's a reason for that. Now, what I want to do is look at LP and LR. So in this case, LP is 8.65 feet and LR is 27.5 feet. Now, we have an LB of 30 feet for this problem. So if LB is 30 feet, what does that mean? We are in zone 3. We're in zone 3. Does that make sense? I'm doing that a little quick. I just want to make sure that everybody's okay with that. All right, I'm going to take that as a yes. Again, if y'all have any questions, make sure you throw them in the chat, turn your mic on. I want to make sure everybody's interactive. Okay, so whenever you're in zone 3, it's not hard. You just kind of have to roll up your sleeves and do it. So when you're in zone 3, you have to go to the W-shaped section, and there's some properties that you're going to need, okay? And it's not hard. You just have to look up some stuff and chug it out. I'm going to show you what you need. What you're going to need is you're going to need the section modulus. You're going to need this, okay? So this is the W14 by 61. I'm on page 1-24 and 1-25. So you're more than welcome to follow along with me if you need. We're also going to need some of these properties over here on the right that you probably have never used before. We need this RTS and this H0. We need J, and I think that's it. Let me make sure I'm not speaking out of turn here. It would help if I was in the right chapter in the manual. Let's see. So SX, H0, RTS, and J. Yeah, that should be it. So we have SX is 92.1 cubic inches. Let's see. It's RTS is 2.78 inches. H0 is 13.3 inches, and J is 2.19 inches to the fourth. So just so everybody knows what these properties are, SX is just your section modulus. RTS is kind of like a radius of gyration for LTB. It's a specific property that you just compute based off everything else. H naught is the center to center spacing of your flanges. So if you go from the center of your top flange to the center of your bottom flange, that's what that height is right there. So it's a little bit different than your depth, a little shorter. And J is just your polar moment of inertia. J is usually a pretty small number. Now, don't forget that for this beam, a couple of things. CB was given to be 1.5 and LB was given to be 30 feet. Now, one thing you need to do with zone 3, convert that to inches. Because what you're going to be doing is computing an L over R. And for L over R, the R is the RTS. And so since RTS is in inches, the LB also has to be in inches so that the units are copacetic. Now, here's the expression. So the first thing we have to do is compute our critical buckling stress. It's a little nasty. So just bear with me. So the critical buckling stress is, there's a fraction out here, CB pi squared E divided by a slenderness squared, okay? And then we're going to multiply it by this expression 1 plus 0.078. There's a fraction multiplied by that slenderness squared, and all that is under a square root. It's a little nasty, but it's plug and chug. So one of the purposes of today's lecture is I want everybody to do this one with me to make sure you're getting the same answer that I do. So we just chug this out. So well, actually, let me see if I can put it over here. So we have 1.5 pi squared, 29,000 KSI. I'm not going to be able to fit this. That's not going to work. So maybe if I can do that. That way I can see my section properties. So 1.5 pi squared, so 360 inches over 2.78 inches squared, and then 1 plus 0.078. So we have 2.19 inches to the fourth. C is 1 for I shapes. SX is 92.1 inches cubed, and then H naught is 13.3 inches, and then 360.278 squared, and all that is under a square root. Now, while you all are chugging this out, if you look at your units, there's a lot of fractions, okay? And if you look at a lot of your fractions, the units cancel. For instance, if you take a look at that big one in the brackets under the square root, you have inches to the fourth on the top, and you have inches cubed times inches on the bottom, so the units cancel. All the L over R expressions, they're unitless. So your only remaining units in the problem are actually that. So whatever your answer is, it's in KSI. So let's see if we can chug this out. So Okay, I'm getting 46.779. Is anybody else getting that? This is definitely one where I could use the second for sure. Okay, good. This one takes a little while. Good. Yeah, it's not hard. It just takes a little while. So, but that's the hardest part. Like I said, there's no real design aid to help us through this one. We just kind of have to chug it out. Once you get the critical buckling stress, you can compute the nominal moment capacity pretty easily. So in order to determine the nominal moment capacity, the first thing that we're going to do is compute that. Because remember, the nominal moment capacity is the minimum of this and MP. So this is 0.9. This is 46.779 KSI. And this is 92.1 inches to the third. Now, one thing about moments, if you look at this, what's going to happen is this is in KSI times inches cubed. So if you just raw compute this, you're going to get an answer in inch kips. What we're going to do is we're going to multiply it by this to get an answer in foot kips. So we're going to take 0.9 times that times 92.1 divided by 12. It would help if I did that properly in my calculator. And so that should be 323.13 foot kips. And then the other thing that we need is that. Good. And so the other thing that we need is this, because the capacity is limited to phi MP. And if we look up phi MP, what do we get for a W14 by 61? Phi MP is 383 foot kips. So the capacity is the minimum of these two. And so the minimum of those two is that one. All right, I'm going to take a sec. I'm sure you all are probably trying to catch up with me and whatnot. I want to see if anybody has any questions on that. Okay. All right. Now, what I want to do now is introduce the concept of design, because up until now, when we've done design for beams, we've only done continuously braced beams. So how did we design a continuously braced beam, right? We would go into, here, I'm going to turn I'm going to stop my share and go to my, my webcam here. So how did we do design, right? So what we would do is we would do the structural analysis to get MU, and what we would do is go into this table, right? And we'd say, okay, here's my moment, go up and find the bold row, and that's what we would do. And that's how we would design. But the problem is with that is this table, or that method only works if the beam is continuously braced. Well, what if it's not continuously braced? What if it's discretely braced? How do we design? Well, unfortunately, this table isn't going to work. We're going to need another aid. So let me go back to my PowerPoint. And before I go into this, I actually have some slides with some animations. So if there's anything that doesn't come through on the recording, let me know. But you might want to watch with me on the recording or watch the screen as we're doing this, because I'm going to do an animation to try and make it a bit clearer. So we're going to be using table 310. So while I'm talking, you might as well turn to table 310. It begins on page like 392, but you really don't get the guts of it until you turn a few pages in. But I want to talk a little bit about what's going on. As you're turning into the manual, it probably looks like a nightmare the first time you see it, but it really isn't that bad. But let's talk a little bit about this. So first off, I want to bring this up, okay? So this is the curve that we use to determine the capacity of a beam according to its lateral torsional buckling capacity. In the end, all that flowchart stuff that we did, all the equations that we're using is really just a representation of this. We're looking at LB on the x-axis, finding our term on the y-axis. That's really what we're doing. This is the Ltb curve according to AISC. Well, if you remember back in column land, we had a column curve, right? Remember, we had the slenderness on the x-axis and we had the critical buckling stress on the y-axis, and then it sort of went like that. And we said, if you're in inelastic buckling range, your capacity is this, and if you're in elastic buckling range, your capacity was that. Now, with columns, there was one curve, and the curve could be used for every column, right? Because the curve was only a function of one parameter. It was a function of the radius of gyration. So as long as you had that, you could use the same curve for every column, which is why the main design aid that we did basically just said, here's how long the column is, here's the capacity, here's the length, here's the capacity, et cetera, et cetera. And the design aid was pretty simple. The problem with beams is that this curve is kind of complicated. Look at all of the parameters that go into the curve, right? You've got the section modulus, the J value, the RTS, you've got the ZX term that's in there, you've got LP and LR. All of those are unique parameters for each beam. And so there is a unique curve like this for every shape in the manual. Every shape has a unique Ltb curve. So there's no way to use a single curve for every beam. So the way the manual gets around that is this. This is every curve plotted on top of one another, okay? So on the x-axis, you have the unbraced length, and on the y-axis, you have the capacity. And it looks like a mess. I know it does, but promise you, it's actually pretty easy to navigate. A couple things to note, though, that are really important, okay? Number one, the FY is 50 KSI for this aid, and that's fine really for our purposes. But one real big one that's going to matter in our design land is that CB is assumed to be 1. If you look at the top of the curve right there, you'll see that CB equals 1, and that is what this chart assumes in design land. For us, when we start going into design, that is where the iteration is going to come. The higher the CB value, the more chance that we're going to have to iterate. The iteration is actually really easy, but if you have a really high CB value, it can admittedly get a little frustrating, but I've got some shortcuts to help make that a little easier for you. Now, what I want to do, and this is where the animation's coming into play, is I want to show you how this table works. I want everybody to watch the slide. But before I do, is everybody able to find this table in the manual? Is there anybody having a hard time finding it? This is definitely a tab section. Like, put a sticky note in your manual if you haven't done this. Okay, I'm assuming everybody's found it. It's, like I said, it starts on page 3-92, but it goes a little bit further from there. So let me show you how this works. Everybody watch the screen here. Okay, so if you want to use this table, first thing you have to do is you have to divide out the effects of CB. So if you're looking at a given beam, if you're doing the structural analysis, like let's say some of the problems that we did today, if you're in design land, what you would do is compute your maximum moment, and whatever your segment is, you would divide out the effects of CB. So this table assumes a CB value of 1, so you divide that out. What you do is you then go into the table where, with the x-axis, go into the table and find the LB for your design, and on the y-axis, your maximum moment with that CB value divided out. Then what you do is you look up and to the right, and you find the first solid line that's plotted, and that's your shape, okay? So for example, watch my little animation here. So we have let's say we have an unbraced length of 28 feet, and let's say we have a maximum moment after we've divided out CB of something like 1162. So what we would do is we would find that point. So you can see that's where LB is 28 and the MU is 1162. And what we would then do is look up to the right. Any section that's in that blue region is a viable candidate, because any section in that blue region is going to be able to withstand a higher bending moment, and it's going to have a longer LB. So any of those sections work. What we then do, you all went dark. Okay. What we then do is we go up and we find the first solid line that we see, and that's the section that we would use. So we would try a W27 by 146, because you can see right here, there's the label. Now, I want to talk a little bit about why we go to the solid line sections. If you remember in the ZX table, we would find our section, but then we would go to the bold row. We went to the bold row because that was the lightest section in that region. That's the same thing that's going on here. When you look at these regions, the solid line sections are the most economical shape in that region. But because of the complexity of the equations, that doesn't always match up to the bold rows, which is why in that last example, we did an analysis of a section that wasn't a bold row. Because when you go back and check them, you might be looking at a section that's not bold, okay? Does everybody have any questions? Is everybody okay on this? To close us out for today, to end our lecture, I want to do a practice. There's no example problem with this. I just want to make sure that we're comfortable using table 310. So I'm going to go back to my notebook here because I have this pulled up. I want everybody to see if they can find the lightest shape with this. I want to look at an LB value of 14 feet and an MU over CB of 2150. So what you got to do is you got to flip this table is, got a few pages to it. On the bottom page, look for LB of 14. And as you advance through the manual, the moments start to decrease. So start to find the graph where the bending moment is about 2100 on the blue line, or on the blue side, and then your LB is 14 feet, and see if you can find that lightest shape. That's sort of what we're doing for the next little bit. I'm going to stop my share and pull up my notebook here because I have this populated in one of my notebooks, or one of my pages. But okay, somebody got a W21 by 223. Check and make sure that you're using the solid line, not the dashed line. So first off, I'm on page 3-99. What I'm going to do is I actually have that page copied right here in the manual, or in the notes. So what we're going to do, we're going to see if this works. We're going to do a, let's do this. Let's go to 14 feet. Something like that. And then 2150 is probably going to be something like that. Right? So then what we're going to do is we're going to draw up. And so that's the section that we want to use right there. And if you follow that up a little bit higher in the page, you can see that's a W40 by 167. I know that the labels kind of overlap a bit, which is why they usually show up multiple times on multiple pages. I'm not giving you a homework assignment on this part today. You don't have to worry about this. I just want to make sure that today you're kind of comfortable with the aid, because starting on Friday, we're going to start using this aid and actually start doing some design. But is everybody else able to find the W40 by 167? Do you all kind of see where we're getting that? Okay, good deal. Any questions before we call it for today? Like I said, this aid really isn't that bad. And if you look in the FE reference manual for steel design, you will find a snippet of this aid. So this is something that you could do on the exam. All right, I am going to go ahead and call it then. I'm going to stop our recording. If anybody has any questions, let me know. You have a homework assignment where I'm giving you basically a single shape, and I want you to compute the capacity with two different sets of LB and CB values. So it's just practice on computing the capacity. I think you'll find it's pretty straightforward. I'm going to stop the recording. That's all I have, everybody, and I will see you all on Friday.